Okay, anyway. So let's talk about acids and bases. So we're going to look at 3 different definitions for acids and bases. The first one we're going to look at is the Arrhenius definition. This is sort of the most restrictive definition of an acid and base. I can't remember what years Arrhenius was working in. It might have been the 1700s, but sort of playing around with what acids form in when you put them in water, what they do, how they affect electricity. I believe that was the experiment. And then what Arrhenius ended up finding was that when you put an acid in solution, it forms a proton, H+, AQ in parentheses, and Cl-. Okay, so HCl, this is a strong acid, hydrochloric acid. Notice the AQ and not the G, so you can have hydrogen chloride gas, right? HCl, hydrochloric acid, as long as it says AQ. So we put HCl in solution, it breaks apart, it's an electrolyte, it forms H+ and Cl-. Okay? Now is a great time to get out a post-it note or index card and write your list of strong acids and strong bases and put it somewhere where you're going to look at it every day so you can memorize those. Right? Because if you can recognize a strong acid or a strong base, we solve those problems in a much more easy way than we solve those problems, same problems for weak acids and weak bases. So if you can identify the strong ones, it makes your life easier. Okay? So Arrhenius definition basically says that an acid produces H+. And I'm showing 2 different ways to write this equilibrium, well, which I've shown as, actually this is not an equilibrium, I take that back. This is not an equilibrium because this is a strong acid, so it completely dissociates. HCl completely breaks apart to H+ and Cl-. So the single reaction arrow towards the products is correct. But we can also write the equation showing HCl plus H2O forming H3O+, aqueous plus Cl-. And we refer to H3O+ as the hydronium ion. So you'll hear me using that word. So I guess sort of a tangential, the same definition but different species produced. So Arrhenius definition is you either produce proton, H+, or hydronium ion, H3O+, when you add the acid to water. Okay? The problem with the Arrhenius definition is that it only works for acids and bases in water. That's very limiting. We're going to see other cases where we probably won't see that many cases where we're not in aqueous solution, but there are instances where that's the case. Arrhenius also has a definition for a base. So if we take lithium hydroxide, another strong base, in solution it will form lithium ion and hydroxide ion. Hydronium and hydroxide sound very similar. Let me make sure you know the difference. And we don't typically show a base reaction with water. We don't do like LiOH plus H2O because you end up with H2O plus Li plus OH. So we don't typically write it that way. Okay, base produces OH minus. So again, like I said, the Arrhenius definition for acids and bases is too limiting, only works in aqueous solution, And for bases, it only allows for one kind of base, which means it must produce OH minus. So there are other bases, for instance, and so we need a new definition. So then Bronsted-Lowry came up with the definition for their acids and bases, or they came up with their definition for acids and bases. And this has to do with the movement of protons. And so H plus. Okay. So BL is for Bronsted-Lowry. Bronsted-Lowry acid donates a proton, meaning it gives it up. And a Bronsted-Lowry base accepts a proton. Means it forms a bond. What's nice about this definition, again, it doesn't require OH minus to be present for the base. We'll show you a really common example of that. And allows for non-aqueous solutions. If you take organic chemistry, you'll do a lot of acid and base chemistry, and a lot of times you're working in non-aqueous conditions. Okay. So just going over it again, Arrhenius acid donates H plus or H3O plus, or gives up H plus. Arrhenius base produces OH minus. Bronsted-Lowry acid donates a proton, very similar definition. Bronsted-Lowry base accepts a proton. Okay. The Bronsted-Lowry definition for acids and bases incorporates all of the Arrhenius definition. So it's sort of, so if this is the number of things that fall into the Arrhenius definition, the number of things that fall into the Bronsted-Lowry definition become larger. And our third definition is going to be the Lewis acid base. And it's going to be more encompassing than all three of those. What's that called? The hierarchical, there's a word for that. I'm really bad at recalling words. Yeah, you may have noticed. Anyway. So again, looking at our hydrochloric acid reaction. Here we have HCl donated a proton to H2O. Okay, I can't remember. There's a way of drawing this that makes the organic chemists happy, and I never remember. So the HCl is going to donate a proton to the water to form H3O plus. So this is another good reason why we write with the acid plus H2O, because now you can actually see that a proton is being donated to something. And then, so we form H3O plus and Cl minus. So what role does water play in this reaction? Is it an acid or a base? It's a base, exactly. Because we said that the Bronsted-Lowry definition of a base is something that accepts a proton. So in this case, water is accepting a proton from the acid. Okay? Yeah, base. We're also going to start using terms like conjugate acid, conjugate base. So the conjugate acid or base shows up on the product side. Sort of just a naming sort of convention that we follow. So if we have an acid on the reactant side, it's going to have a conjugate base on the product side. The other term we're going to use is conjugate acid-base pair, meaning they're related to each other by a difference of one proton. But let's go through this. So chloride ion has lost a proton. All right. HCl donated a proton, so HCl is the acid, which means that the chloride ion is the conjugate base of HCl. Okay. And H3O plus is the conjugate acid of water, in this case, because it has accepted. So water has accepted a proton, which means it acts as a base, as we said. So it's going to have a conjugate acid on the product side. So we're going to, if there's an acid on the reactant side, it's going to have a conjugate base on the product side. And it's going to differ by one proton. Yeah. It's just one proton. Can't be more. Let's see. We'll go. Let me do an example. Shane just asked if a conjugate acid-base pair only differs by one proton. The answer is yes. And is it only always one proton? The answer is still yes. But let's say we have H2SO4. Okay. This is a strong acid. Well, the first proton is strong, so it easily forms HSO4 minus. Okay, I'm leaving off all my aqueous phases. So in this case, HSO4 is an acid. It's donating a proton to water, which I also didn't draw. And then the conjugate base is HSO4 minus. But one of the interesting things about H2SO4 is that it has two protons that it can donate as an acid. Okay? So HSO4 minus can further react. It can form H plus in solution and SO4 2 minus. In this case, HSO4 minus is acting as an acid. And the conjugate base of this acid is SO4 2 minus. Okay. So, H2SO4 and HSO4 minus are conjugate acid-base pairs. HSO4 minus and SO4 2 minus are conjugate acid-base pairs. But H2SO4 and SO4 2 minus are not conjugate acid-base pairs. And that's because they differ by more than one proton. Okay? It takes two equilibria to go from H2SO4. It takes two reactions to go from H2SO4 to SO4 2 minus. Other questions? My next example is. Here. So I wanted to just show H plus, proton, hydronium ion. I essentially use these interchangeably, although please recognize that the structure of proton and hydronium ion are very different. So our hydronium ion is H3O+. Of course, our proton is H+. We can even set up a reaction to show that H+ plus water forms H3O+. But when we're writing our acid-base equilibria, I will sometimes write H+ is formed, or sometimes write H3O+ is formed, okay, just so you know. Questions on any of that? All right, I think on Friday we'll play a game on conjugate acid-base pairs. I can only have 100 of you log in at a time, so we're going to have partners. I'm not paying for this. But we'll do something fun on Friday. See you all. Have a great rest of your day. Okay, so we're going to start thinking a little bit about the strength of acids and bases. And I mentioned that knowing the difference between the strong acids and weak acids and strong bases and weak bases is incredibly important because we approach solving problems related to those differently. When it's a strong acid, strong base, the problems, we can solve them usually easier. So if we look at sort of the relative, all right guys, calm down a little bit. Thank you. If we look at the relative strength of the acids, this table is showing our strong acids. They're not all listed, but many of them are there. And you'll see that right after the list of strong acids, H3O+ is listed. And so this is our hydronium ion. It is fairly strong in terms of its acidity. And then we have a series of weak acids and water, and then some things that can technically transfer protons, but it doesn't happen to any great extent whatsoever. So with our strong acids, you'll notice that they fully dissociate, so we're going to use a single arrow to the product side, which is how I've written the HCl reaction here. For our weak acids, they do not completely dissociate, so we use our double arrow to represent equilibrium. Then if we look at the conjugate bases of those acids, and that's essentially what this second column is showing. So here's our HCl, the conjugate base is Cl-, and we look at the strength of the base itself. The base strength is increasing as we go down this list, which means that those species that are really strong acids produce very weak bases. So they very rarely, very little react with water to produce an acid, okay? So for instance, if we put HCl in water, we're going to get Cl-. We don't see Cl- reacting with H3O+ to form HCl. That's what that is saying, okay? However, if we take something like, let's do SO4 2-, I can write it on there. SO4 2-, so we put it in solution with water. It will have some amount by which it can act as a base and form HSO4-. And OH-, all of those aqueous, well, except for the water. Okay, so that's what we're thinking about when we're looking at relative acidity and basicity. Something like CH3- is a very strong base, will react with water to form CH4. Okay, the auto-ionization of water is a really important reaction. And so basically what this says is that water can react with itself, and it can form H3O+, hydronium ion, and hydroxide, OH-. Okay, so if you have this reaction, in your notes real quick, write the equilibrium expression for that reaction. KW, or K equals what? So recall that we don't include solids and liquids in our equilibrium constant expressions. So you should end up with a K of H3O plus times OH minus. And this is a special equilibrium constant expression that we write for water, and we typically will give it call it the KW value. Is everyone okay on that? Okay. So, given that we have our Kw equals the concentration of H3O plus times the concentration of O minus, we can find a value for this, and this value is temperature dependent. At 25 degrees Celsius, it's 1 times 10 to the minus 14. And so what we can do, knowing a value for Kw, is we can calculate a concentration of H3O plus or OH minus. So you'll notice that if we were to set up an ice table, let's go ahead and do it. We'll do our 2H2O in equilibrium with H3O plus OH minus. Initially, we don't have any H3O plus or OH minus to speak of, okay? So when we're setting up something like this, yes, if you have a beaker of water, there is already H3O plus and OH minus in that beaker. But in our thought experiment, initially we're saying we're starting with pure water, we have no H3O, no OH minus. So what happens then? That water is going to react with itself to form some amount of H3O plus and some amount of OH minus. And so at equilibrium, we'll have X moles per liter of H3O plus and X moles per liter of OH minus. And so we can set that equal to our Kw value, just like we do with our equilibrium, other sort of more general equilibrium problems. So equal to X squared. You want to see that? So if we plug our X values in here, we get X squared. And if we solve for X, take the square root of both sides, we're going to get X is equal to 1 times 10 to the minus 7 moles per liter. Questions on that? This relationship is going to be very important. We're going to use that a lot in our calculations for pH. Oh, yes?
Sorry, so since you said it was temperature dependent, like, how would we know when it would change based on temperature?
Yeah, so if you're working in problems and it doesn't specify the temperature, I think it's safe to assume you're at 25 Celsius if K is 1 times 10 to the minus 14. If concentration, because if we want to find we found our concentration of X, right? And so X is equal to the concentration of OH minus, which is equal to the concentration of H3O plus. I'm going to kind of skip over the next slide and just put everything here. And this, when we have the concentration of hydroxide and the concentration of hydronium ion equal to each other, that is a neutral solution. That is the definition of neutral. So therefore, neutral. When H3O plus equals the concentration of OH minus, the solution is neutral. Why am I stressing that and not saying page 7 is neutral, right? Well, we're going to work a problem, and let's do that next. in a problem and it tells you, give you a different value for K. So you would have to be given that value. Which is, I mean, it's very likely that you'll see something like that, to be honest. You'll see it in the homework and on exams. So we basically solved what is the OH minus. The temperature has changed. It's going to, okay. Let's say, let's take a look at this reaction. It's known to be an endothermic reaction, meaning it requires heat to happen. Okay, we saw this with Le Chatelier's principle. We said that it's useful to include heat as either a reactant or a product for an equilibrium when we're thinking about the effect of temperature on that equilibrium. It's endothermic, and so heat is a reactant in this case. So if we add more heat, which direction does this reaction shift? Yes. Shift towards the right, or towards the product side, okay? And that means we're going to form more H3O plus and more OH minus. Okay. So let's look at the example, actually working out some of the math. So for our Kw at 25 degrees Celsius is 1 times 10 to the minus 14. At 50 degrees Celsius, it's 5.5 times 10 to the minus 14. So it has increased in value. Okay, still small, but it has increased. So at 25 degrees Celsius, we found that the H3O plus and the OH minus concentration were equal to 1 times 10 to the minus 7. So now if we look at what is the concentration of H3O plus and OH minus at 50 degrees Celsius, we can solve the problem the same exact way. We can do an ice table. Again, we don't include liquids and solids in our equilibrium. We can ignore those concentrations. We're going to have X moles per liter of both products, not initially. Sorry, I jumped to the end. X moles per liter of H3O plus and OH minus at equilibrium. And we said that at 50 C, Kw equals 5.5 times 10 to the minus 14, which is equal to the concentration of H3O plus times the concentration of OH minus, which is equal to X squared. And so to solve for X, we take the square root of both sides. We'll get X is equal to 2.35 times 10 to the minus 7 moles per liter. Which is then equal to the concentration of H3O plus and OH minus. They're both the same. And so is that solution neutral? Yes. Okay. Yep. Yes. In pure water, it will always be neutral at any temperature. But I think the key thing that I'm not showing is the pH value. So let's do that. So to calculate pH, pH is just a way of stating a hydronium ion concentration. We're going to do more of this in a little bit, but you've probably seen it, maybe. pH is equal to minus the log of H plus, or H3O plus. Same thing. So, which means we can take our H3O plus concentration and plug that in to solve for the pH. So at 25 degrees Celsius, pH is minus the log of 1.7 times, 1.0 times 10 to the minus 7. which is equal to 7. For 50 degrees Celsius, pH is going to be equal to minus the log of 2.35 times 10 to the minus 7. Let's see. Does anyone have their calculator out? Want to solve that for me? Yeah. 6.63. That's fine. Okay. So the pH is decreased and it's below 7. But that solution is still neutral. Okay? So even though the pH, you've been sort of trained to think that pH equals 7 means the solution is neutral, I'm telling you now that's kind of a lie. Okay? If you're not at 25 degrees Celsius, at 50 degrees Celsius, pH of 6.63 is neutral, because that's simply taking minus the log of the concentration of H3O plus in a neutral solution. So the definition of neutral has nothing to do with the actual value of the pH necessarily. It has to do with if the H3O plus and the OH minus concentrations are equal. Yeah?
So for like the ice table, if you have like 2x or something, but still nothing for the first column, like can you tell before you put numbers in if it's neutral or not then?
So you mean if this were 2x and not x squared?
Yeah, like if different coefficients.
Oh, the water's special, so we're only going to see this type of equilibrium for this.
Okay.
Yeah. And we're really only thinking about whether water is neutral at this pH, I guess. Maybe I need to be more specific. This is specifically for water. Yeah.
Why is the pH of the negative log of the hydrogen ion the same as the negative log of H3O? Or am I just misunderstanding?
Oh, because we essentially use H plus and H3O plus interchangeably. So you may have seen pH equals minus the log of H plus. Typically that's how people remember the equation if they do. But we're saying that the number of H plus is equal to the number of H3O plus.
Oh, okay.
Yeah.
Is H plus always interchangeable with H3O?
Is H plus always interchangeable with H3O plus? Yes. For our purposes for acid-base chemistry, yeah, it's going to be interchangeable. Yeah. Other questions? These are good. Okay. So the next slide sort of summarizes this relationship, where we're just looking at water forming H plus or H3O plus in solution. Neutral solutions, we always have H plus or H3O plus equal to OH minus, but only at 25 degrees does that mean the pH is equal to 7. Okay? If the, let's see. Now, the other thing to note here, so if we are at 25 degrees Celsius, okay, and this is typically where we're going to be thinking, if a solution has a pH that's less than 7, it's acidic. The concentration of H plus is going to be greater than 1 times 10 to the minus 7. The concentration of OH minus will be less than that. Okay? That ratio is going to hold. And then basic greater than pH 7. H plus is less than 1 times 10 to the minus 7, and OH minus is greater than 1 times 10 to the minus 7. So that sort of thing, at 25 degrees Celsius, that's probably what you've sort of been remembering about pH from previous experiences. Sound good? All right.